All right, so listen up, guys. Last thing in this unit is efficiency. Efficiency is a pretty straightforward concept. All right, efficiency is a measure of how much of the energy used to do a job actually gets the job done. Okay, because we know nothing's 100% efficient. Okay, the second law of thermodynamics says that energy is going to flow from the high energy object to the lower energy area or system or whatever. Okay, so we know we're constantly losing energy when there's a conversion, and we saw that in our lab last week. Okay, we saw that, I mean, nowhere near the amount of energy that was present at the beginning was present at the bottom of the ramp. Okay, it lost a lot of energy on the way down, and that was a simple energy conversion. Right? So to make things efficient is a challenge, and we want to make things more efficient because we don't want to waste energy. Now, some examples of places where we're trying to make things more efficient. Okay, and there was kind of a big kerfuffle about all of this when the government brought it in, but they said they would replace all the light bulbs in your house with LEDs. Okay, and that, there's a good idea behind that, or at least at least kind of a good idea behind that, in that, yeah, LEDs use a lot less energy than conventional filament style, like Thomas Edison style light bulbs. Okay, they use even less than the compact fluorescent, and the advantage they have over compact fluorescent is they don't blow up. Okay, I had 2 compact fluorescent bulbs blow up in my house and nearly burn my house down. So yeah, I'm kind of off of those a lot. Okay, they also had what in them? All the compact fluorescents, a lot of mercury in them, so they weren't good to throw away. So they, yes, they used a lot less energy than the Thomas Edison filament style bulb, but okay, they still had their kind of drawbacks, right? LEDs are pretty environmentally friendly, and you can replace a 60-watt tungsten style light bulb, okay, with a 4-watt LED. Why can they do the same job but use so much different amounts of energy? Okay, in what way? Like, what does it not produce that the other one does? Heat. Yeah. Okay. Like you can plug in an LED bulb, and I actually just did this on the weekend. Okay, I had one that one of the diodes had gone in it, and it was just flickering. So it was, while it was on, I reached up and unscrewed it and pulled it out, and it was cool to the touch. Okay, you try that with a traditional light bulb, and you just burn your fingers, and probably the bulb shatters too. Okay, so you don't want to touch one of those while they're hot, okay, or while they're on. They produce a lot of heat. They're called an incandescent bulb. Incandescent means to produce light with heat. Okay, so when the electricity flows through a traditional tungsten filament bulb, okay, that little filament it just gets really, really hot. Okay, tungsten is very resistive. That means it doesn't let electricity flow through it very easily, and as a result, a lot of heat is produced. Okay, and it glows white hot and produces light at the same time, right? But uses 60 watts. Okay, that's 60 joules per second. Okay, 60 joules of energy per second for a traditional 60-watt bulb. Okay, whereas a 4-watt LED is using 1/15th that amount of energy. So if you were to replace all the bulbs in your house with LEDs, okay, you would notice a pretty significant savings, especially in December, okay, on your power bill. Everyone kind of with me there? All right. We're also looking at efficiency in other areas, right? I mean, light bulbs are something that we have to have on, especially during the wintertime. Okay. Another place, our car. Okay. I mean, we all probably used a car in the last 24 hours, most likely. Okay, maybe 1 or 2 of us didn't, right? But most of us, at least in some way, shape, or form, used an internal combustion engine in the last 24 hours, right? Well, internal combustion engines, even though they're getting more and more efficient, are still really, really inefficient. Okay, they produce a lot of heat. That's how they run. Okay, they make the gases get hot, and the expanding gases can push the piston down, and that's what creates the forces that move the car along. So there's kind of no way around that except to find places within the car that are wasting energy and make them better. The process by which power is generated can't really be made that much more efficient. We have to blow gas up in order to make the car run. Okay? So if we're looking at just like a typical, let's say, like sedan, let's say, or small compact SUV, okay? We're looking at the amount of energy consumed by the exhaust system. So let's say you put $100 worth of gas in your car. Okay, and most cars won't take that, but if you drive a truck, you can do more. Okay, let's say you put $100 worth of gas in there. $33 of that gas goes out the exhaust pipe as heat. It didn't do anything. It just went out the exhaust pipe. That's why you can't just grab the exhaust system when the car is running. It gets really hot. Okay? It's essentially taking all the spent gases from the combustion of gasoline and venting them out the back or back side of the car. Okay? Why do we want to do that? Not so much that we don't suffocate, because we could still breathe. We'd just be breathing in poisonous stuff like carbon monoxide and we would die. Okay, so we don't want that, obviously. Okay, so the exhaust system vents it to a more convenient place. Okay. The exhaust system is also responsible for making your car not so noisy, unless you're Redneck Joe with his truck that doesn't have any, mufflers on it. So it's got the straight pipes or the glass packs or something fancy. Okay, that rips up and down the road in front of my house. Okay, yeah. Then they're not doing their job as much. Okay, they're still venting the spent gases, but they're not quieting the car down. Okay, so 33%. Okay, so you've burned 33 of your $100, and you haven't gone anywhere. All right, cooling and heating system. Your car is so inefficient that it needs to use 1/3 of the money you put into it in gas in order to keep itself from melting down. Okay, so when your car is running and the pistons are moving up and down, obviously they move the drivetrain that turns the wheels. But there's also pulleys and other drive shafts that come off of it that help to run the other systems of the car, okay? Namely, the cooling system, right? So there's a belt that runs off that turns the fan on the radiator, okay? And there's a belt that runs, sometimes it's the same belt, that runs down to a little pump that circulates the coolant throughout the engine in order to keep the engine cool and not melt down, okay? So all of these things pull a lot of energy, okay, and they're going to use a lot of that. So it's collecting the energy and it's venting it, this time out the front of the car. So we got heat going out the back, we got heat going out the front. Right? There's so much heat produced, and what does heat do? Not a lot. Okay, it's not doing any useful work. It's just being gotten rid of, okay, so that the car doesn't destroy itself. All right, the drivetrain. All right, so drivetrain, there's friction within the drivetrain. Okay, there's metal parts that are in contact with each other, sliding past each other. Okay, and 10% of the energy in your fuel is lost there. Okay, your accessories, 4%. Accessories would include things like windshield wipers, rear window defogger if you have one of those. That's a high draw electrical application actually. Your stereo, your interior lights, headlights, tail lights, brakes, okay, all of that kind of stuff. Is a hydraulic pump that runs the brakes, okay, all of those kinds of things would count as kind of accessories, okay. If you have one of those like giant stereos, because Redneck Joe with his glass packs has also got like a giant stereo that like signals the end of the world, the apocalypse is coming, okay. He's got the big, I don't know, like 20-inch subs in the back, yeah. So anyway, when you've got that much extra accessories, they produce an extra electrical draw because they're drawing electricity. Okay, where does the electricity come from? Well, it can be drawn from the battery, but the battery always has to be charged. So there's actually a little generator called an alternator in your car. It's another thing that runs off of a belt that steals power from the car. The more it runs, okay, the more power it steals. Okay. Back before computers controlled the idling and stuff like that in cars, when you would turn on or turn up your stereo or turn on the rear window defogger, you would watch the RPMs, that's the engine speed drop, okay, because they would start to pull more energy in other directions, and you could actually, if you were going to race somebody, not that anyone would do that, you would turn off all those accessories, the air conditioner, all that kind of stuff, because it was all drawing power away. The battery is just there to really start the car. Okay, because the car isn't running to generate any power. So the battery is there to start the car, and then after that, the alternator provides electricity for all the electrical devices in the car. If the alternator goes, then you'll get the battery light will come on. It doesn't mean your battery is dead. It just means it's not charging anymore. And that can be that your battery is dead, or it can be that there's something wrong with the alternator and it's no longer charging. If that happens, eventually your car will just stop because it will draw electricity from the battery to run the spark plugs, to do all the electrical stuff in the car until the battery's dead, and then the car will just die. Okay, then you have to get the alternator replaced. Not always the battery. The battery will most of the time recharge. Okay, so accessories, another 4%. Internal friction, that would be actually within the engine itself, is another 6%. Okay? And we're getting better on that. That number drops all the time because we make better and better lubricants, okay, for motors. Now we have like completely synthetic oils that are much better in low temperatures and things like that, and they reduce internal friction. That not only lengthens the life of the car, but makes it more efficient. Okay? And then here's what we're left with. Useful energy that drives the automobile forward, 14%. Okay, now these are older numbers. I mean, cars are a little bit more efficient now. Let's say, the average kind of 4-cylinder small sedan car might run at about 20, 21. Okay, something like that. Not terribly efficient. Okay, like you wouldn't, if you felt sick, you wouldn't go to a doctor who was only right 14% of the time, right? Okay, I mean, but we accept on a daily basis 14% as an acceptable number for something we use all the time. Okay, and you wouldn't think that, no, that I totally wouldn't accept something that was paying me back 14%. That's not right. Okay, but we do it all the time. Okay? It's just not a very efficient system. Okay, so systems with moving parts lose energy as heat. The more times you convert energy from one form to another, the more energy you lose, because no energy conversion is 100% efficient. Okay, so every time there's a conversion from one form to another, some energy is going to be lost. So one way to increase efficiency is to have less conversions, right? That's one of the reasons why electric cars are more efficient than gasoline engines. There are less energy conversions. Electricity is directly converted into mechanical energy in an electrical engine. Okay? Whereas in a gasoline-powered engine, chemical energy is converted to heat, okay, which causes the expansion of gases, which then converts to mechanical energy, which is converted several times along the drivetrain before it gets to the wheels. Right? That's lots of energy conversions. Lots of energy gets lost. Okay? If we're looking at like generating electricity, right? In Alberta, we for the most part, use coal. Right? Well, that involves burning coal, which is used to boil water, okay, to turn it into steam. Okay, so there's one energy conversion. Okay, well, actually, that's two: chemical to heat, heat into like potential energy in the form of steam, and then that steam can turn a turbine. So there's a conversion of that kinetic energy to another type of mechanical, and the turbine then turns a generator, which is another energy conversion that produces electricity. Okay, so the more times we convert energy, the less efficient it becomes. All right. Okay, so according to the second law of thermodynamics, heat flows from hot to cold. It can be made to do work if we can put something in between. Okay. However, during the thermal energy transfer, some energy is always lost to the surroundings, so the efficiency of a system can never be 100%, and that means you never come close to getting the energy out of a system that you put into it. Okay, you just never do. All right, so the formula for efficiency is this, and it is on your formula sheet. Okay, percent efficiency is the useful work output. That's the work the machine actually did, divided by the work input. That's what you had to put into it. Okay, so the amount of work that actually got done, divided by the amount of energy required to actually do it. Okay, and then multiply by 100. Okay, I usually take that part out just because it's easier to not have it. You can do that part in your head and just move the decimal 2 places over. Okay, so when we do that, okay, it's basically EM divided by EI. So mechanical work, okay, divided by input energy or whatever you want to say. Okay, but it's the work done divided by the energy required to do it. That gives us our percent efficiency. That's a good question. Honestly, I don't have a really good answer for that one. I don't know what the most efficient thing we have is. It would probably be quite simple. It wouldn't be a complex machine, right? Hmm? No, I wouldn't say a bicycle is all that efficient. I mean, when you're riding a bike, can you hear it? Like when you're pedaling it? Yeah. And there's rolling friction on the ground, and yeah. I mean, certainly it's not as inefficient as an internal combustion engine, but walking would probably be more efficient than biking. But I don't know. No, because even to do that, it's going to lose some energy to other forms. Okay, like let's say you have a heater, right? Yeah, that's the one you brought up. It probably has a fan, right? The fan make noise? That's not running 100% efficient, right? Noise wasn't something you were looking for. Okay, look at a speaker then. A speaker is meant to make noise, but a speaker moves back and forth like this. That's kinetic energy, right? It's going to lose some energy in the process of doing that. Yeah, there's never anything that's, even when I'm just saying, oh, I'm going to light a fire to make me warm. Well, fires make noise and light, which wasn't really what you were going for. You wanted to get warm. You have to look at, yeah, the energy's all there. I'm just saying it's never doing all of what you want it to do. Okay, so some machines or systems involve the conversion of mechanical energy from one form to another. So like a crane uses mechanical energy to do the work of lifting a load vertically to the top of a building. Well, a crane uses an internal combustion engine. Okay, so it's burning this fuel in order to move the motor that pulls the load up to the top. A lot of energy is going to get lost in the process, but the load will eventually get to wherever it's supposed to go. We only look at the energy gained by the load because that was the job we were trying to accomplish. Okay, that'll be our top number. Okay, so we got, right, our mechanical divided by the input. This would be the energy gained by the load. This would be the energy that was consumed by the crane. Okay, the crane is going to consume more energy than the load gains in being lifted in the real world.
What if you had, like, what if you had a machine that was very, like, did all the work you needed to do and didn't lose much energy, but you needed, like, an insane amount of input? Would that be efficient, or would the input just lower the percent?
Well, the efficient, if, like you say, if it's turning all of that input, even if it's a colossal value, into a useful work, then it's still efficient. It's just doing a lot, right? Efficiency is just a percentage. It doesn't look at, how much did you put in and you got lots out. It's a matter of how do they compare, right? Did I get a percent? How much of that percentage did I actually harness to do useful work? Okay, so automobile internal combustion engines run anywhere from 12 to, let's say, upwards of 20. Okay, an electric engine can be up to 95% efficient. Right? There's not as many conversions along the way, and there's less internal friction in an electric motor because the magnets repel each other and keep the pieces from being in contact. The only place where there's actually any mechanical friction is where the drivetrain is kind of in the housing. Okay, there'd be bearings there, but that would be about it. Everywhere else, okay, doesn't really touch, so that's much more efficient than metal pistons moving up and down inside a cylinder, okay, rubbing on each other. That's not efficient at all. Okay, a steam reciprocal engine, okay, 50 to 75%. A steam turbine engine up to 40%. So those work a little bit better, but it's a matter of how are you making the steam. Okay? Usually making the steam is the most inefficient part of a steam engine. Okay? If you're using nuclear power, well, that might be a little bit more efficient because you get a lot of heat out of nuclear power and you can kind of harness it all, but yeah. All right, so let's look at this example here because we talked about a crane just a minute ago. Okay, so we got a crane that lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work, or mechanical energy input. So this is the energy that the crane required, and it only did 8,000 joules of useful work. Okay, so this was the energy gained by the load. How can I tell the difference? Okay, the power of 10. Which number is always going to be the smaller one? The output. Yeah, the output's always going to be the smaller number. So if you're ever in doubt, like the wording of the question is confusing, and this one is a little bit, okay, always look, the smaller number is the one that goes on top. Okay. Yep. Yeah, you might have to manipulate this equation, but this equation is easy to manipulate because efficiency, like we said, is just going to be, right, the mechanical energy output divided by the mechanical energy input. Okay, the input number is always going to be bigger. Otherwise, what are you doing? If you have something that runs at 120% efficiency, what's it doing? Making energy, creating energy, and breaking the first law of thermodynamics. So if you can do that, good for you. You're going to get filthy rich. But you won't be able to do that. All right. So if we're looking for the percent efficiency here, okay, we're going to take our 8,000 joules because that's the amount of useful work that the thing did, okay, and we're going to divide it by the 23,000 joules, okay, worth of energy that were required to do the 8,000 joules worth of work, right? When we divide those, we're going to get 0.348. okay, which is 34.8%. Everybody all right with that? If I need to manipulate this, right, it's pretty straightforward. If I want to solve for EM, I just multiply EI over to this side. Okay. If I want to solve for EI, I just swap it with EF, right? Just that's like V equals D over T. You've manipulated far more difficult equations than that one.
So there might be a question where it's like you have to solve for mechanical energy using like final initial kinetic potential and then use this?
No,
Okay.
not in this course. No. Eventually, maybe. Okay. But no, I won't make you do that yet. What I would say is I would give you, this would be the kind of question you would get, be worded like this, or it would say, this thing runs at this efficiency, how much energy was actually needed to do the 8,000 joules worth of work? Something like that. Okay, everybody all right with how that one works? Yeah. Yeah, and you can leave it as a decimal. I'm fine with that. I don't like the whole multiply by 100 thing because it's just one more part of that equation that I don't think we really need. Okay, 0.348 is also a percentage. Just leave it at 0.348. You're dividing joules by joules. It technically doesn't have any units. Yeah. But if you put a percent sign, then you got to put it as 34.8. Right? The percent means that it's over 100. Right? So, yeah, if you leave it as a decimal, I'm good with that. If you want to make it a percentage, then make it 34.8%. This doesn't get a percent sign. If it does, it means it's 0.348 out of 100, and it's not. Right? Okay. I want you guys to try these three here. Okay, I'm going to give you a few minutes to get ahead of me, and then we'll have a look at them. Okay, so in this first one here, we got an efficiency of 15%, which as a decimal looks like this, 0.15. And that's how you have to put it in mathematically. Okay, it's used to do 3.2 times 10 to the 4 joules of useful work. Top or bottom number? Top. Useful work is the top number. Okay, calculate the mechanical energy input that had to be supplied by the combustion of fuel. All right, so we know that efficiency equals, okay, our useful mechanical energy output, okay, divided by our input energy. So this is what we're looking for. So we're going to just cross multiply with efficiency. Okay, so we've got that EI will equal the mechanical energy divided by the efficiency. And when you divide by a decimal, the number gets bigger. Okay. All right, so we're going to take our 32,000 joules and divide that by 0.15, and that should give us 213,333.33 joules worth of energy required to do that work. On the test, these problems will only be in the multiple choice. So, however it looks in the answers. Yeah. All right, how are we doing on number 2? Okay, how many people are done 2? Okay, so yeah, number 2 is you just plug in the numbers, right? Okay, give you a little bit more time on 3, and if you're done 3, try 4 and 5. Look at it here. All right, so on number 8, we know that the efficiency is 0.35. They told us it's 35%. They're saying, what's the input energy? That's the bottom number. Okay, so we're looking for this number right now. Okay, input energy required if a 2,000 kilogram object is lifted 5 meters. Well, how much energy is required to lift something in a perfect world to that height? Mass times g times height, right? We just have to change its, just have to find the potential energy it would have at 5 meters. In a perfect world, that's exactly how much work you would have to do. In the real world, we're going to have to do more. Okay, so we go m times g times h. So we go 2,000 times 5 times 9.81. Okay. All right, so we got 98,100 joules. All right, so that is our useful work that was done because it's how much we changed the energy of the load by. Okay. Now what we need to do is find EI. Well, EI is on the bottom. Can I solve for it here? What do I have? Where do I have to move it? Right, I got to move it over here. I got people that are multiplying, and I'm not sure where that's coming from. Okay, I need to move EI over to the other side by multiplying both sides by it. Now, what do I do with efficiency? Divide it. All right, so my input energy will be the useful work that was done divided by the efficiency of the work. All right, that way I'm dividing by a decimal and I get a bigger number. So 98,100 joules divided by 0.35 will give us our 280,285. Okay.
That's a lot. Like, I don't know, like how many joules am I using to lift my phone?
Not very many,
Like 10.
maybe. Yeah.
I don't. So that's a lot.
Yes. That's why we don't use joules. We use kilojoules a lot or megajoules. Like it's just, yeah, it's, yeah. Or gigajoule sometimes even. All right. Everybody with me there? Okay. What's that? Yep. Yes, you can.